So tomography defined as sense diffusion is the title of my talk, and obviously it is bringing together tomography and sense diffusion. So we'll have to start by saying what is sense diffusion, and that can be the subject of a very long discussion. Now, I'm offering to your attention two definitions of sense diffusion. The first one is from 2002. That is an excellent PhD thesis from Melvin Reich. And then we fast forward to 2016, and the reason why I put that date is because this is a book that was just recently published at CRC, has said that it's year 2016. As you can see, the definition has grown 3 times in length, and even if you look at the short definition, it's not terribly useful. I'm not saying it's wrong, but if you look at it, you'll see that you have to read it several times in order to make sense of it and in order to take something for yourselves. So if we take the Occam's razor and we clean the words, what we can probably say in the end is that sense diffusion is the use of sensor data to achieve better data or information. So what I've done here, I've done the focus of kind of encapsulating all this into just one word. So I haven't done much. I haven't done anything useful, because even if you had this button on your keyboard, that wouldn't have been useful either. Putting something like that in Google wouldn't give you anything. So in order to ask kind of myself to provide a definition for you, I would like to define sense diffusion and its functionality. So I want to offer to you the 3 C's, which are classifications of sense diffusion, and they are there on the screen. Concurrent fusion, which achieves better accuracy or robustness. So that is, you take a measurement, you measure, and then you average it with the kind of code that there is white noise and you're trying to improve signal to noise. Collaborative fusion is bringing new information, it's giving you emerging views, and you always use the same measurement but in a different context. Say, for example, when you do triangulation, you use exactly the same measurement, but you position all your sensors spatially in such a way that you read something new. The same happens with stereo vision. Then you have 2 cameras, and I'm going to show you that exactly the same thing happens with indirect imaging, which is tomography. Complementary fusion is also something that everybody knows, and biometrics is one of the areas. When you combine the information that you have on a fingerprint and a retinal scan in order to achieve the result of recognizing whom they belong to. And this inertial sensor result of the GPS, for example, is a good example of sense diffusion of this kind. We are going to concentrate mainly on collaborative fusion, and I'll try to convince you that tomography, in its main application, it is a collaborative fusion task. Okay, so in terms of applications, in terms of the 3 A's, which are again related to functionality, we are looking at the sense diffusion tripod, architectures, algorithms, and applications. I don't have time to discuss architectures, and they are not so relevant to what I try to convince you, but I will spend some time in showing you what are the algorithms for sense diffusion white tomography, and the trivial ones, which are Kalman filtering, central limit theorem, and Bayesian. They are joined by something that are known as inverse transform algorithms. In terms of applications, obviously, there are many, and amazingly here, the blue bars are your smartphones. So you can see how much of sense diffusion happens in your pocket. So that's quite an interesting thing to see. So what I'm going to also add to those applications is indirect imaging, which is another word for tomography. Okay, so time for tomography. Now we introduced sense diffusion as much as we could. So now what is tomography? Tomography definition is much better and much easier. It is an indirect imaging method, and its name already tells you what it is. It comes from tomie and graphos, which is cutting or slicing, and of course making a written account of that cutting or slicing, which is also, the word also means scribe. The sense of all this definition is that with carefully chosen measurements at the periphery of an object, one can produce the image of a cross-section. If we want to be a little bit more precise, the reduction of that cross-section is unobtrusive and often without contact. And of course, the image of the cross-section can be otherwise inaccessible, as it is in this picture. You don't want to image people stand by cutting them, because usually they are alive. So performing an inverse transform where the sensing task is the sampling of the forward transform and the production of this image is the inverse transform of what we do. How do we define that? Just bear with me for a couple of slides and you'll be convinced. The way the main modality for tomography works is X-ray CT. So we have a radiation source, we have some beams coming out of the source crossing an object, which in this case I present as a two-dimensional slice, and we have a radiation detector, which looks at the intensity of all those beams as they cross the object. So, what happens here we are able to record the shadow of this object as the X-ray pass through it. So for each projection angle, theta, the tomograph records the projections, which are these blue functions. So we are having projections which are a function of the angle, and of course of this coordinate, which enumerates the detectors. Therefore, the object, which is normally represented by the function of x and y, is represented by all the data acquired in the form of theta and t functions, which is obviously pointing to something which is a transform. So if you have three angles, for example, the picture becomes a little bit more difficult to trace, but anyway, they are all shadows of that object at a particular angle. So if you want to do collaborative measurements between these detector arrays, you would need to have as many parallel beams as possible and as many projections as possible in order for the transform to be complete. So, as a summary, we have an object which is available in X and Y. We transform that object into the area, into the space of theta and t, so therefore all possible projections will constitute a transform of this object, and if we measure this, then by the fusion algorithms you would be able to come back and generate this X and Y picture. So this is called the radon transform. The forward radon transform is the sensory task, and the inverse radon transform is the fusion task. This is a mathematical and graphical expression of the fusion. So in the center you have the two-dimensional Fourier transform of our object. Now this is two-dimensional spatial transform, it's not the time. That's why it's two-dimensional. So you have the two-dimensional representation of our object. What the Fourier slice theorem says, and that is the main algorithm, is that if I take all those shadows, all those projections at angle theta, I make a one-dimensional Fourier transform, I would be able to populate this two-dimensional inverse transform at those angles at which the projections were taken. Therefore, if I have some kind of a sampling of that two-dimensional Fourier transform, I would be able to make an inverse two-dimensional transform and get my object. So this is the simple algorithm. It's not, of course, so simple in practice, but this is what it is. There is at least one analytical solution. Now I'm showing you this in order for you to see what I mean by collaborative sensors. Now, these are individual sensors which are staying here at this fan, looking at the propeller, which is imaged tomographically. So when you rotate all this, you would have many angles for this fan. Therefore, the single projection is made of collaborative sensors, while the Fourier slices, which are in the two-dimensional transform of your object, are complementary. And we need as many of them in order to solve the task. How can we use this view tomography as sensor fusion? Now, this is a sketch of a dual modality tomograph which images the three-phase flow in a pipe. You have gas, you have liquid, and you have solid, and you apply two tomographies. One is electrical tomography, which is extract conductivity. Therefore, what you will get as a contrast is water, because water conductivity is 82, everything else is much less. Now, if you do also X-rays on the same object, you will have solids plus liquids as one, because the density is similar against void or gas, which is much less density. So, in order to make the three phases in one, you have to take two pictures and you have to put them on top of each other. And you need to have some method of registration of those images. Otherwise, there is no way that you will know how to do that. It's not photography as in, divide forces in the center that have mass and have supermass together. This is much more difficult. So it is possible, however, to avoid this complementary fusion with good understanding of the contrast generation in tomography and the nature of the inverse problem. So we can do that by handling the unusual contrast, for example, working in secondary contrast, which means that we reconstruct an image in one parameter, but then we recalculate the same image at a low level of error into another space, into another parameter. Or we can use contrasts which already have the information fused, and that is the interesting thing of what I'm going to show in the end, because that is sensor fission, it's not sensor fusion. Okay, so let's go quickly. First, I want to show you what is a path integral and why it's so important. So if I have this picture of my object, as I explained, and I try to write the mathematics, which is fairly simple, I found out that the minus logarithm of the number of photons that have been detected here divided to the number of photons that have been emanated from the source is going to be an integral of the density of this object. And that is Beer-Lambert's law, actually, those of you that recognize it. Now, if I write this formula instead of the Beer-Lambert's law, this is what X-ray tomography gives me. Now, what I'm going to do, I have 2 minutes more, yeah? What I'm going to do, I'm going to write to you the delay of a pulse that propagates through some kind of a method. So that is equal to 1 over the speed of electromagnetic waves times the refractive index. If you look at those two integrals, they are mathematically absolutely equivalent. So if I know that this is sensor fusion, this should be also giving me sensor fusion. And that's exactly what is being done here in the context of stereophase tomography, and Miguel is sitting down there. This is his work. So we have styrofoam phantoms, and we measure the delay of pulses, of stereophase pulses, through these styrofoam phantoms, and this is what we get as a result. Now this might seem a little bit hairy image, but I have to remind you that 1 pixel here is only 3 wavelengths. So it's a very good result. A second example of unusual contrast is this guided path tomography case. So I have to really be able to drive this. Okay, so what I'm going to do now, I'm going to show you 2 integrals again, with the old one that you know, and then the new one, which is resistance in a wire. Mathematically, they are absolutely the same. These are path integrals. So if I treat the path integral here from the specific resistance of the wire, that can be a function of temperature. And there you are a secondary contrast. So if I reconstruct the resistivity of my wire in space, I would be able to recalculate the temperature field. This is another example where instead of using electrons through wires, I use photons through an optical fiber. And that is the magic carpet that we have done in Manchester. It uses only 3 projections, uses 120 line integrals, and gives you these results. So again, another unusual contrast. And this is just a quick reminder of what we do when we want to measure several parameters of the field. So this is a jet engine, and if you do tomography at the exhaust, it's comparatively simple because it has close to atmospheric pressure. But if you want to use it to do that in where the combustors are, it's very difficult because you have 2,000 degrees, etc. Now, this is what's my last kind of show to you. This is the function that shows what is the area under the spectral absorption line when you look at water as a combustion product. Now, this is dependent on temperature, on concentration, and on pressure in a very convoluted way. So the question is, if we make images, if we do tomography of this function, then probably by some kind of a fit, we would be able to extract those 3 fields. How possible is that? Of course, everything is a question of how many, can I stop this? How many fields you image and how many measurements you take. So this is hyperspectral approach. We have all those images of temperature in 42 colors, and we fit the absorption lines with a function that is dependent on temperature, on pressure, and on concentration. So this is the result. You can see that The error here is 2.5% because the fitting procedure has been optimized for temperature. It's a little bit worse here for concentration, but you can solve the optimization process so that the error here is minimal and here you don't care. It is similar for pressure, but pressure usually doesn't get subtracted. So this is the end of my talk. There is no free lunch because I achieved all this by making very convoluted spectral measurements. And my last thing that I want to show is this. It is Charles Fowler's 7th law. It is inspired by multi-sensor concepts in military systems, and this very clever guy said, be wary of proposals for synergistic systems, because most of the time when you want to make 2 plus 2 make 5, you don't get 5, you get 3, and sometimes you get 1.9. This is officially published in 79 in Affiliation. So what this guy actually said is that when you try to do synergy and oversubscribe yourself, usually you don't achieve the result you want, so it's not 4, it's less than 4. And if you're not careful, actually you ruin where you started from. So thank you very much. Sorry, I'm a little bit longer than what I thought I should be. Thank you.